Morning, Commander. Welcome to today's class. Today we'll discuss significance of dimensionless terms. Okay. In the previous class we solved examples on dimensional analysis. There we found out different dimensionless terms. Okay. Out of those dimensional terms, some of the terms will be very useful in model studies. Okay. We will discuss the significance of those dimensionless terms in today's class. So in that, the first one is flow coefficient, which is also known as capacity coefficient or specific capacity, which is identified as pi1 is equal to q divided by ndq. Okay, which signifies the volume flow rate of fluid through a turbo machine of unit diameter of runner operating at unit speed. Okay, the specific speed is constant for dynamically similar conditions. That means if you consider any two machines, let it be model or prototype, these machines are dynamically similar, then the flow coefficient will be equal and they are constant. Okay, which is represented as, here this is the flow coefficient of machine 1 and this is the flow coefficient of machine 2. Q1 divided by N1 D12 is equal to Q2 divided by N2 D2, which is equal to constant. Okay, this condition can be applied for dynamically similar conditions. That means if any two machines are dynamically similar, then we can consider the flow coefficient like this. Okay, hence for a fan or pump of certain diameter running at various speeds, the discharge is proportional to the speed. This is the first fan law. That means in this equation, for a certain diameter of pump running at various speeds, then the diameter will be remains constant. Q is directly proportional to N. Okay, this relation we call as a first fan law. That means here, as the speed increases, the discharge will also increases. Okay, this is the first fan law. Next, dimensionless term is speed ratio. Okay, the speed ratio is derived from the flow coefficient only. So here we know the flow coefficient q divided by nd2, which can be written as like this. The q can be written as, that is flow through a circular pipe, can be written as area into velocity. The cross-sectional area of the pipe is pi d square by 4. Okay, see here pi is constant, pi and 4 is constant, so then you can write it as q is directly proportional to d square v, that means d square v. Okay, so instead of here, instead of q, you can write it as d square v. Okay, see here the d square d cube will be get cancelled. We have v divided by nd. Okay, the tangential speed of rotor, that RP, can be calculated by using the equation u is equal to pi nd. Here pi is constant, so u is directly proportional to nd. Okay, so instead of nd you can write it as u here. So this equation will become v by u. Okay, thus that can be written as 1 by 5. Okay, here phi is the speed ratio which can be determined by u by v. Okay, here u is the tangential velocity of the runner or rotor, v is the theoretical jet velocity of the fluid. Then the speed ratio can be defined as the ratio of tangential velocity of the runner to the theoretical jet velocity of the fluid. Okay, for a given machine, this speed ratio is fixed. That means if a machine running with a fixed flow of fluid, inlet flow, okay, then the speed ratio is fixed, considered as a fixed. Okay, next dimensionless term we discuss here is end coefficient or specific speed. Okay, which can be identified as pi2 is equal to gh divided by n square d square. Okay, here once again the nd can be written like this way, that is nd is proportional to u, tangential velocity of the rotor. Okay. So in place of n square d square, you can write it as q square. So this head quotient will be proportional to gh by u square. Okay, which can be defined as it is the measure of the ratio of fluid potential energy in terms of column height h, that is this is the potential energy, and the fluid kinetic energy while moving at a rotational speed of the wheel u. That means this is kinetic energy of the fluid which is rotating as the same speed of the wheel velocity. Okay, this is the head quotient. Here also for two dynamically similar machines, the head quotient is equal and remains constant. Okay, that can be written like this. That is gh1 divided by n1 square d1 square is equal to gh2 divided by n2 square d2 square, that is equal to constant. Okay. See here for a specified diameter, the head varies directly as the square of the tangential speed of the wheel. This is known as second fan law. That means here for a specified diameter, d will be remains constant for a given machine. G is acceleration due to gravity, which is constant. So here h is directly proportional to n square. That is the head produced by the machine, which is directly proportional to the square of its speed. Okay, this is the second fan law. Next, dimensionless parameter, which is power quotient, or which is also known as specific speed, which is identified as phi 3 is equal to q divided by rho n cube d to the power of 5. Okay, which represents the relation between the power, fluid velocity, fluid density, speed, and wheel diameter. Okay, here also for dynamically similar machines, the power quotient will be represented like this. This is for machine 1 and this is for machine 2. Okay, that is P1 divided by rho n1 cube d1 to the power of 5, that is equal to P2 divided by rho n2 cube d to the power of 5, that is equal to constant. Okay, for a given machine, that means if the diameter is constant, the density for a given fluid which is also constant, then power is directly proportional to n cube. This is what we call third fan law. Okay, see, power is directly proportional to n cube. That means the power produced by the machine, which is directly proportional to the cube of the speed of the wheel. Okay, this is what we call third fan law. Say this is one of the purpose of dimensional analysis that we have discussed. That means one of the purpose of dimensional analysis is to produce the fan laws. Okay, where the fan laws will be used in order to transfer the performance of model to the performance of prototype. There we will use these fan laws. Okay. Next, dimensional analysis. Dimensionless parameter, that is Reynolds number, which is identified as phi 4 is equal to mu. That is the Reynolds number is derived from the dimensionless term, that is phi 4 is equal to mu divided by rho nd square. This you can be split like this, rho nd into d. Okay, whatever the d square is there, that you can be written into nd into d. Okay, which is proportional to mu divided by rho ud. That means nd is proportional to u here. That is u is equal to pi nd. Pi is constant here, or we can write it as u is directly proportional to nd. Okay. So in place of nd, we can write it as u. U is nothing but tangential velocity of rotor or wheel. Okay. But from the speed ratio phi, we have the equation u by v. We have the ratio u by v. Okay, phi is fixed for a given machine. Okay, which is also constant. Then u is directly proportional to v. U is nothing but tangential velocity of wheel. V is the theoretical jet velocity of the fluid. Okay, so in place of u, you can write it as v. Okay, u divided by rho vd can be written as reciprocal of Reynolds number, that is 1 by re. Okay, or the Reynolds number is equal to rho vd by v. This is the equation for the Reynolds number. Okay, this Reynolds number is one of the dimensionless parameter from which we classify the nature of fluid flow. Okay, we can classify the nature of fluid flow into two types, that is turbulent flow and laminar flow. Okay, if the Reynolds number is greater than 4000, then the flow is termed as turbulent. Okay, for the turbulent flow, always the inertia effect is more than the viscous effects. That means here the Reynolds number, which is defined as the ratio of the inertia force to the viscous force. Okay, if the Reynolds number is greater than 4000, okay, that means in the turbulent flow, always the inertia effects is more than the viscous effects. Okay, here the inertia force is, how to define the inertia force? How to define the inertia force? Inertia force is nothing but a force produced due to momentum of the fluid. Okay, the inertia force is nothing but force produced due to momentum of the fluid. Okay, what is the meaning of viscous force? How to define the viscous force? Which is the force produced due to resistance between the fluid layers. Okay, the viscous force is nothing but force produced due to resistance between the fluid layers. Okay, that means in the turbulent flow, always the inertia effects is more than the viscous effects. Okay. Next, if the Reynolds number is less than 2000, the flow is termed as laminar flow. Okay, in the laminar flows, always the viscous effects are more than the inertia effects. Okay, this is the classification of fluid flow based on the Reynolds number. Now we will discuss the effect of Reynolds number on the turbo machines. Okay, the turbo machines means we need to discuss both on the power generating turbo machine and power absorbing turbo machine. Okay, that means if you consider for the turbines, that is power generating turbo machine. Okay, these turbines use relatively low viscosity fluids like air, water, light oil. Okay, these are having less viscosity. So the effect of Reynolds number is negligible in case of turbines, or we can say it as only a little effect. The Reynolds number will affect only little on the performance of turbines. Okay, but if you consider power absorbing turbo machines like small pumps, compressor fans, and blowers, here these machines will add high viscous fluids. Okay, so the performance improves as an increase in the Reynolds number. That means if the Reynolds number increases, the viscous effects will be reduces. That means if the viscous, whatever the fluids used by these machines, their viscosity will be decreases, then the performance of the machine will be improves. Okay, this is the effect of Reynolds number on turbines as well as on the power absorbing machines like pumps, compressor, fans, and blowers. Next, we have specific speed. Okay, this is also a dimensionless term which is very important in incompressible flow machines. Incompressible flow machines means the machines which will handle the fluids. Okay, like water or any oils. Okay, that will be known as incompressible flow machines. Okay, so this is that specific speed is only the parameter that does not contain the linear dimension of the runner. You just observe the previous dimensionless parameters what we have discussed. Either the Reynolds number, we have the linear dimension d. Similarly, power quotient, which is also having linear dimension d. Aid quotient, which is having the linear dimension d. Next, we have the flow quotient, which is also having the linear dimension. Okay. See how the specific speed differs from other dimensionless term is this parameter does not have the linear dimension of the runner. Okay. Because of it, if any two machines operating under the same conditions of flow and head, and if they are geometrically similar, then they will have the same specific speed irrespective of their sizes. Okay, whatever their size may be, if the two machines are geometrically similar and if they are operating under the same conditions like flow and head, then they will have the same specific speed. Okay. See here, the specific speed will be expressed in different terms for power generating turbo machines and for power absorbing turbo machines. See, for power absorbing turbo machines, the specific speed mainly expressed in terms of Q, that is discharge. Okay. For power generating turbo machines like turbines, the specific speed will be expressed in terms of P. Okay. Now we will discuss specific speed of a pump. Okay. How to define the specific speed of a pump here? Okay. So which is defined as the speed of geometrically similar machines discharging 1 cubic meter per second of water under a head of 1 meter. Okay. This is the definition of specific speed of a pump. Okay. What is the definition of a specific speed of pump? It is a speed of geometrically similar machine discharging 1 cubic meter per second of water under a head of 1 meter. Now we need to derive the expression for specific speed of a pump. Okay. First we will consider the head coefficient. Okay. What is the head coefficient? GH by n square d square. Okay. Or you can write it as n square d square is directly proportional. That is phi 2 is a constant. N square d square is directly proportional to GH. Okay. This equation we have to express in terms of d. Okay. Then what is d square? Which is proportional to GH by n square. Okay. Or what is d? D is equal to root of GH. D is proportional to root of GH. That is nothing but 1 by 2 divided by n. Okay. Next, we will consider flow coefficient. What is the flow coefficient? What is flow coefficient? Phi 1 is equal to Q divided by NdQ. Okay. Or you can write it as Q is directly proportional to NdQ. Okay. See, the specific speed which does not have the linear dimension. That means which does not have the linear dimensions like diameter, length, breadth, height. Okay. So here we need to eliminate the d. Okay. See, in place of d we will substitute this value in this equation. Okay. Why we have considered flow coefficient here? Because the specific speed of pump will be expressed in terms of discharge. That's why we consider the flow coefficient. Okay. Yes. Then what is Q is directly proportional to, in place of d we need to substitute this value. Okay. What we are going to get? N into GH whole to the power of 1 by 2 divided by n whole to the power of dq. Okay. So then what is Q, which is directly proportional to n? GH to the power of 3 by 2 n power of 3. Is it right? Or you can say it as Q is equal to, introduce a proportionality constant here, let it be C. Okay. C is equal to, that is n GH to the power of 3 by 2 NQ. Okay. Here we need to find the value of C, that is proportionality constant. Is it right? How to find? Yes.
N square.
Yeah. N will be get cancelled. N square. You can simplify here. Okay. Then what it will become? Yeah. N will get cancelled with Q. N square we have. So N square. Okay. We need to get the value of C here with the definition. Okay. What is the definition of specific speed of a pump? Geometrically similar machine discharging 1 cubic meter per second of water under a head of 1 meter. That is nothing but if the discharge is 1 meter cube per second, if the head is 1 meter, then the speed will be equal to specific speed. Okay, that is from definition. If Q is equal to 1 meter cube per second, H is equal to 1 meter, then the speed is equal to specific speed. Here the specific speed will be represented as N suffix S. Okay. Then what is the value of Q here? 1 C. H value is 1. So G to the power of 3 by 2. N will become Ns square. Then what is the value of C? What is the value of C? C is equal to Ns square by G 3 by 2. Okay, this is the value of C here. C value has to be substituted here. Okay, then we will get the value of Q. Is that? Okay, see here the value of proportionality constant C is equal to Ns square by G by G to the power of 3 by 2. Okay, the value of C will be substituted in this equation. Then what we have here, Q is equal to Ns square by G 3 by 2, G to the power of 3 by 2 into G to the power of 3 by 2, sorry, GH whole to the power of 3 by 2 divided by N square. Okay, here G to the power of 3 by 2, G to the power of 3 by 2 will get cancelled. Okay, so what we have, Ns square H to the power of 3 by 2 N square. Okay, we need to get the value for specific speed. Then what is specific speed? Ns square is equal to Q N square H to the power of 3 by 2. Or what is Ns? It is a square root of Q N square H to the power of 3 by 2 square root. Okay. Then what we have here, that is N square will be get cancelled in square root of Q H to the power of 3 by 2 whole to the power of 1 by half. That is, if you write square root in terms of that is half. Okay. Then what it will be? 3 into 1 3, 2 into 2 4. So what is the power? 3 by power of 4. Okay, this is the expression for specific speed of pump. Okay, understood? Next, we will discuss specific speed of a turbine. Okay, next, what is the definition of specific speed of a turbine? Which is defined as speed of geometrically similar machine which produce 1 kilowatt of power under a head of 1 meter. Okay, this is the definition of specific speed of turbine. Okay, the specific speed of turbine is speed of a geometrically similar machine which produces 1 kilowatt of power under a head of 1 meter. Okay, see here the power, the specific speed of turbines expressed in terms of power. Okay, that's why we need to consider power quotient. Okay, to derive the expression for specific speed of a turbine, we have considered flow quotient because the specific speed of pump is expressed in terms of discharge. Is it right? So here yes, what is the power quotient? P divided by rho n cube d power of 5. P is directly proportional to rho n cube d to the power of 5. Okay. Here also we should eliminate d. Okay. That is from the end quotient. Already we have got this relation in the previous derivation. Okay. D is directly proportional to gh to the power of 1 by 2 divided by n. Okay. Here also we use the same relation from the end quotient. That is D is directly proportional to gh to the power of 1 by 2 divided by n. Okay. Then what is P is directly proportional to rho n cube. D means gh to the power of 1 by 2 n whole to the power of 5. Okay. So P is directly proportional to rho n cube gh to the power of 5 by 2 n to the power of 5. Here n cube will be get cancelled with n to the power of 5. Okay, by 2 times. Then what we have here, P is directly proportional to rho gh to the power of 5 by 2 divided by n square. Okay, here also we introduce a proportionality constant C rho gh to the power of 5 by 2 divided by n square. Okay, here also we need to get the value of C here. Okay, which is obtained from definition of specific speed. Okay, what is the definition of specific speed? What is the definition of specific speed? It is a speed of geometrically similar machine which produces 1 kilowatt power under a rate of 1 meter. That means if power is equal to 1 kilowatt, it is 1 meter, then speed is equal to specific speed. Okay. As substitute in this equation, power is equal to 1 kilowatt, C rho gh is 1 ns square. Then what is the value of C? ns square rho g to the power of 5 by 2. This is the value of C. Okay. Now we will substitute the value of C in this equation. Yeah. Okay. Then what is then power is equal to C value we have ns square rho g to the power of 5 by 2 into rho gh to the power of 5 by 2 divided by n square. Okay. See here, rho get cancelled, g to the power of 5 by 2 will get cancelled. So P is equal to what we have here, ns square h to the power of 5 by 2
divided by
n square. Okay. In terms of specific speed, what it will be? ns square is equal to Pn square h to the power of 5 by 2. Okay. And what is specific speed? It is the root of Pn square h to the power of 5 by 2. Or ns is equal to n into root of P h to the power of 5 by 4. This is the specific speed of turbine. Okay. So one thing you should be keep in mind while calculating the value of specific speed for pump and also for turbine. Okay. What are the units will be used to derive these expressions? Okay. What is the units are used to derive the expressions of specific speed of pump and specific speed of turbine. See, in calculating the specific speed of turbine, the value of n should be in RPM. Okay, that means the unit of n should be in RPM, P should be in kilowatt, n should be in meter. Okay, these are the units we use to calculate the value of specific speed of a turbine. Similarly, for specific speed of a pump, n root of q divided by x to the power of 3 by 4. Okay, here the unit of n should be in RPM, q should be in meter cube per second, x should be in meter. These are the units you need to follow to calculate the specific speed of pump. Okay. Next we'll discuss significance of specific speed. Okay. First we will discuss significance of specific speed in pumps. Okay. So generally in incompressible flow pumps, it is possible to guess the approximate impeller shape from the specific speed. Okay. This is the specific speed equation for pump. Okay. See, from this equation we came to know that the specific speed is directly proportional to discharge. That means as the discharge increases, the specific speed will also increase. And the specific speed is indirectly proportional to head produced by the pump. Okay, that means as the head increases, the specific speed decreases. Okay, this is the relation we got from the expression of specific speed. Okay, see, from this equation we came to know that small specific speed impellers will have narrow and small openings, whereas large specific speed impellers have wide openings and are expected to have large flow rates. You can check it here. That means when we will have the low discharge, if the opening of a impeller will be having a narrow openings, and when we will get the large discharge, then the impeller opening will be wide opening. If the inlet of the impeller will be wide opening. Okay. So you can see here in the figure we have mentioned different shapes of the impellers for the pumps. Okay, this is the centrifugal pump. You just see here, this is having a narrow opening, so produces a less discharge. That's why we are having a low specific speed. Okay. Next we have a mixed flow pump. Okay. The opening of this mixed flow impeller will be little bit wider than the centrifugal pump, so they can produce more discharge than the centrifugal pump. Okay. Next, finally, we have the axial impellers. Okay. These axial impellers will be having wide openings, so they can produce large discharge. Okay. So they will have the high specific speeds. Okay. That means if you have a side condition, there you need to produce more discharge, but you are not bothered about the head produce. Head produce means to which vertical height you have to pump the water. Okay, to what heights you are pumping the water from the pump. Okay, you have a side condition, there you need to produce large discharge, large amount. That means you need to pump more amount of water per unit ton, but you are not bothered about what is the height of a to which height you are pumping the water. In such cases, we will go for the axial flow impellers. We will select the axial flow impellers. Okay, these impellers will produce more discharge, the less head. Okay, you have the side conditions, there you need to produce high heads. That means to larger heights you need to pump the water, but you are not bothered about the discharge. Okay, then we will go for centrifugal pumps. These pumps will produce us more heads but the less discharge. Like that way, based on the site conditions, whether we need to produce more discharge or we need to produce more head. Okay, we will calculate the specific speed. Whatever the value of specific speed we got, based on that we select the shape of the impellers, whether the centrifugal pumps will be working effectively or axial impellers will be working effectively. Based on that we will select the impellers. Okay, this is the significance of specific speed in pumps. Similarly in turbines also, based on the specific speed we can decide the shape of the rotors in the turbines also. Okay, here we have the three types of turbines. That is Pelton wheel turbine, Francis turbine, axial flow turbines, which is also known as Kepler turbines. Okay, generally the Pelton wheel, which is a low specific speed and high head turbine. That means the Pelton wheels will be work efficiently under low discharge and high heads. Okay. And we have the Francis turbine, which covers a wide range of specific speed and which is suitable for intermediate heads. That means these Francis turbines works efficiently under medium head and medium discharges. Next we have the Kepler turbine, which operates at low heads and need large flow rates. That means these Kepler turbines work effectively under low heads and high discharge. Okay, suppose we have the site condition. Site condition means the site there we need to install the hydraulic power stations. Okay, let it be we have the two site condition. One is Joke Falls, another is Gaganachukki and Barachukki. Let it be the two site conditions we have. There we need to install a hydraulic turbine. Okay, see in Joke Falls, it is a high head. Available head is high because from larger heights the water is falling. In Gaganachukki, Barachukki, the water falling is take place at lower heights. That means the Joke Falls is higher head site condition. Gaganachukki, Barachukki is lower head site conditions. Okay, these are the two conditions. We need to decide which turbine has to be installed. Okay, for that site condition we will calculate the specific speed. Okay, in Joke Falls, head is high. Okay, we will get the lowest specific speeds. Okay, we are not bothered about getting discharge. That means if you have the high head space, you can supply only low amount of discharge for produce the same amount of power. Okay, in Gaganachukki, Barachukki, we have the less heads. Okay, so the specific speed is high. There we need to supply the more amount of discharge. This is the site condition. Okay, for Joke Falls, if you use the Pelton wheel, the Pelton wheel produces the more power because there the site condition is the less specific speed. Okay, if the specific speed is less, the Pelton wheel will be works effectively and it will produce more power. Okay. See here the Francis turbine, which is produces which efficiency is less under this condition, and the Kepler turbine may not work there for that condition. So there, if you use the Pelton wheel, which will produces more power at higher efficiency. Okay. Suppose in the other site condition like Gaganachukki and Barachukki, there we have the low heads. Okay. There we have to use the Kepler turbines in order to produce more power. That is axial flow turbines. Okay, there the availability of head is low. We need to supply the more amount of discharge there. Okay, see here for this higher specific speeds, the Pelton wheels cannot be worked there. The Francis turbine may be worked, but the efficiency is less. Okay, based on the site conditions, the specific speed will be help us to select the shape of the rotors in case of turbines. Understood? This is the significance of turbines. Sorry, significance of specific speed in turbines. Next we will discuss unit quantities. Generally, the unit quantities are determined with the hydraulic turbines. Okay. These unit quantities are obtained when the turbines operate under the unit head, that is H is equal to 1 meter, and here we will assume that the efficiency of a turbine remains same in both the cases. In both the cases means when the turbine is working at unit head, there is 1 meter head, and when the turbine is working at full head. Okay. See, generally we discuss three types of unit quantities, like unit flow, unit speed, and unit power. Okay. Here we need to derive the expressions for these unit quantities. The unit quantities which are also used in our fluid mechanics labs also to determine the performance of hydraulic turbines like Turbine, Francis turbine, or Kepler turbine. Okay. First, we have the unit flow, which is defined as the flow that occurs through the turbine while the turbine is working under a unit head. Okay. See, which is derived from the equation that is fluid flow equation through the nozzle. Okay. Which is Q is equal to A C V root of 2GH. Okay. Here A is the cross-sectional area of a nozzle, CV is the quotient of velocity, G is the acceleration due to gravity, H is the head. Okay, head of the turbine. Okay. Here the only one variable we have, that is H. Okay. The area of a nozzle for a given machine, the area of a nozzle, quotient of velocity, acceleration due to gravity will be constant. Okay. So instead of having so many constants, all are equated to a single constant, that will be K, that is equal to root of H. Okay. Here K means A CV root of 2G. Okay. Here we have the K, that value we need to calculate. Okay, that is from the definition of unit flow. Okay, what is the definition of unit flow? Says when H is equal to 1 meter, what is the flow? Flow is equal to unit flow. Okay, if you substitute these values here, okay, that is Q is equal to unit flow. K root of H 1 meter. Root of 1 means 1 only. Then K value will become unit flow. Okay. This value we need to substitute here. Then what is the flow? Q is equal to K value is equal to unit flow into root of H, or what is the unit flow? Total flow divided by root of H. This is the expression for the unit flow. Okay, this is the total flow. This is the flow through the turbine when the head is 1 meter. Okay. Next, similarly, next unit quantity, that is unit speed. Okay. So here the unit speed is the speed at which the machine runs under unit head. This is the definition of unit speed. Okay, which is derived from the expression that is head flow. Sorry, head quotient. Okay, what is the head quotient? Phi2 is equal to GH divided by L square D square. Okay, or what is the head? It is equal to pi to n square d square divided by g. Okay. Or we can here we need to get the unit speed. Then we need to express in terms of speed. N square is equal to gh by 2 d square. Okay. Here you can write it as n square k into h. See here for a given machine, diameter is constant. So here we have the three constants g, pi to d. Okay, instead of having number of constants, let it be one constant, that is k. Here what is the value of k? K is equal to g speed by 2 d square. Okay. So what is n? N is equal to, let it be like this way only. We need to calculate the value of k. Okay, that is from the definition of unit speed. What is the definition of unit speed? When h is equal to 1 meter, speed is equal to unit speed. Okay. Then what we have here? Nu square, that is equal to k. H value will become 1 meter. Okay. So in place of k, what you can substitute? Nu square. Okay, that is n. Then this equation n square is equal to mu square h, or nu square is equal to n square divided by h, or what is nu? That is equal to root of n square by h, or unit speed can be written as total speed n divided by root of h. This is the expression for unit speed. Okay. Similarly, we have the unit power. See here, what is the definition of unit power? Unit power is the power developed by the hydraulic machine by working under a unit head. Okay. Here the unit power derived from the power equation. What is the power equation? P is equal to rho G to H. Okay. But here we have one more relation. Instead of Q, here we need to eliminate the value of Q here. Okay, instead of Q, in the unit flow equation, what we have here, Q is equal to K into root of H. Okay, so in this equation, in place of Q, we will substitute K into root of H. Okay. Then what is the power equation? Rho G K root of H means it is nothing but h to the power of 1 by 2 into H. P is equal to rho G K. Then what is this? That is half plus 1, 3 by 2. Okay, this is the equation. See here we have the three constants rho G K. Okay, instead of that we will use the one more constant here, that is C, h to the power of 3 by 2. Okay, here what is the value of C? C is nothing but rho G K. This is the constant. Okay, we need to get the value for the C here, that is from the definition of unit power. Okay, what the unit power says, when the head is equal to 1 meter, the power is equal to unit power. Okay, that means when h is equal to 1 meter, power is equal to unit power. So in this equation, in place of P, there is unit power. C, h is equal to 1 meter, 1 to the power of 3 by 2 means 1 only. The constant value will be unit power here. So the C value substitute here. P is equal to unit power h to the power of 3 by 2. Okay. Or what is the unit power? P divided by h to the power of 3 by 2. This is the expression for unit power. Okay.